Section 3.4, Rotating Frames of Reference. In this section, we're going to talk about rotation seen from inertial frame of reference and from non-inertial frame of reference. We're going to talk about fictitious force, which is a centrifugal force, and application at a centrifuges, Coriolis effect, artificial gravity, and roller coaster design. One application of the circular motion are centrifuges. A centrifuge is a rapidly rotating device used to separate substances and simulate effect of gravity. We have seen this device in a medical laboratories when they do a blood test. Another application is a centrifuge for space training. Astronauts and jet pilots lie in a compartment at the end of the large centrifuge for a space training. This centrifuge stimulates gravity in order to train them for a space mission. Here is a situation. There's a rider on a merry-go-round leaning against the handrail as it spins. Definitely, that rider will feel as a handrail is pushing her against her body. When a merry-go-round moves or turns, the rider tends to go straight because of inertia. That's a natural tendency of motion. However, a rail will prevent her from going straight, so it's going to force her to undergo circular motion. The centripetal force acting on her body in this situation is a push from the rail. This force that keeps her body in a circular motion is directed, as you know, toward the center. That's why it's called centripetal force. This is a free body diagram of the object seen from the Earth frame of reference. As you see, object is accelerating, and that acceleration is called centripetal acceleration. Let's consider the same situation from the accelerating frame of reference, or in non-inertial frame of reference, that is a merry-go-round. But now you are the rider. As merry-go-round spins, you feel as you are being pushed to the right from inertia toward outside of the merry-go-round circle. Let me explain that what happened. Let's say for time t1, you are at this point here. And you know velocity vector is always tangent to the circle. So if there's no rail holding you, you're going to go, because of inertia, in a straight line. So you're going to end here at the time t2. However, there is a rail that holding you at this point. So instead of being at this point here, you are being pushed or hauled toward the center by that rail. Centripetal force in this case is that force that rail is pushing you. However, because of inertia, you are being pushed away. So that's why you're ending up at this point here. So this force in rotating frame of reference acting away from the center, it is a fictitious force. It is not existence force. However, this force, which is called centrifugal force, it is used to explain how in a rotating frame of reference you are in equilibrium. You are not moving. Refer to that rotating frame of reference because you are sitting there or you're holding to that rail. Relative to a merry-go-round, you are not moving. So how can we explain that is a equilibrium in that rotating frame of reference? The only way is for the forces to cancel each other. So that's why when you draw a free body diagram of the merry-go-round frame of reference, you're going to see there are forces that cancel each other because literally you are not moving. So that means something has to cancel that rail force that is holding you or is pushing you toward the center. So that's why physicists invented a term or a fictitious force, a fake force, to analyze or to make that equilibrium possible, or to make equilibrium explain. So fictitious force, which is called centrifugal force, comes from the Greek word that Greek word centri means center, and fugal means away, run away from center. So that force, it is directed away from the center. So that's why centrifugal force is a force that is directed away from the center of that circular motion. But is obviously that force does not exist. You're feeling the way because of inertia. And the same situation happens with any object, not just with people. Any object. For example, if you have a ball that is on a spinning platform, the ball is being pushed toward the outside. Otherwise, the ball will fly away. So the ball is being held either from the static force of friction or from something that is holding the ball to undergo circular motion. So centrifugal force, again, is a fictitious force in a rotating frame of reference. So in a rotating frame of reference, that means that frame of reference that is accelerating, or a non-inertial frame of reference. Again, if you do a free body diagram of that ball in a rotating platform, that is going to be the force of holding the ball is going to be canceled by what we call centrifugal force. So that fictitious force that really don't exist, but is the only way that you can explain why ball is not moving relative to that rotating platform. As we talked about why you are not moving relative to merry-go-round frame of reference. So there's a video that illustrates the centrifugal force and centripetal force with an animation and some other explanation. I recommend you to watch that video. I'm going to post that link on the bottom of this video. Centrifuges are frequently used in medical laboratories to separate blood samples. Red blood cells are the densest component of the blood. Centrifugal force will move the cells toward the bottom of the tube. As a centrifuge spins, the particle continues to move in a straight line because the net force acting on it is zero. Because of inertia, it's going to move at a straight line. So it is going to end up at the bottom of that test tube. But how is that possible? As a matter of fact, velocity will carry the particle from point A. Let's see that here is one cell. It is at the position A. And since that is free to move, it is going to move at a straight line because of inertia. But when it moves at a straight line, at a time t2 is going to go at this point here, at a point B. But if you see the point B relative to point A, it is toward the bottom of that test tube. So that's why the blood will end up at the bottom of the test tube, because it's heavier. So heavier the mass of the particle, the more inertial. So more is going to go toward bottom of that test tube, and replacing the lighter one, they have less inertia. So that's why the lighter component of the blood, it is on the top of the test tube. As we know, the Earth's surface is rotating. It is on a rotating frame of reference. So it is a non-inertial frame of reference if you see that from outside point of view. So the rotating of the Earth on its axis creates a centrifugal force on an object on the Earth's surface, especially at the equator, because at that point acceleration is bigger. So the object to undergo circular motion will travel at the bigger distances. So radius is bigger. But the effects are very small, so you don't really feel that much effect. But you can calculate it, and we're going to do that calculation later on. The object acceleration at equator is about 0.34% less than acceleration by gravity alone. So not only you're going to feel lighter because the surface of the Earth at the equator is far from the center of the Earth, as we talked about before, but even if you are there, you're going to feel lighter because it is the tendency to spin you away, to push you away from that rotating frame of reference. At the equator, the magnitude of centrifugal force is at maximum, although it is really very small, but is a maximum possible. So at the equator, you have the gravity that is pulling you down, and you have a centrifugal force that is pushing you up, making you to fly away from the surface of the Earth. So obviously, gravity is much, much stronger compared to that force. So that's why if you are in a equator surface, on the surface of the Earth, you don't really feel much difference as a normal. But yes, it is a slight, very small difference that, as I said, we're going to calculate it later on. So the combination of relatively weak gravitational force because of the distance from the center of the Earth and a strong centrifugal force makes the object lighter in the equator, much lighter than what it is at poles, on the same surface at the poles. Here's another demonstration in a video that you're going to see why the shape of the Earth is like that. Because of the centrifugal force, or basically the inertia that makes those particles of the Earth or to move away from a center more at the equator than at poles. That's why the distance of the surface of the Earth is longer. It's a 12 kilometer away from the center compared to the same position at the poles. I'm going to post that link at the bottom of this video. Here's a practice problem with a centrifugal force. The centripetal acceleration of the object at the Earth's surface at the equator results from the daily rotation of the Earth. Calculate the object's centripetal acceleration given at the radius of the Earth at the equator is 6.38 times 10 to the power 6 meter. So what is given is a radius, and the period is 24 hours for full rotation, and acceleration is required. So we know the formula that involves a period, 4 pi square r divided by t square. Period is for 1 day, for one full rotation. It happened in 24 hours. So, and 1 hour is 3600. So by doing that calculation, you get the period of one rotation is 86,400 seconds. So you can use that in your formula, 4 pi square r divided by t square. You have everything now. Plug those numbers and you get 0.03374. As you see, it is really small. Now, if the reading at the bathroom scale is 588 Newton, so your weight, what would be the change in the reading of the scale, same scale, on the surface of the Earth at the equator? So first you need the mass. It's like a weight divided by force of, which is force of gravity divided by gravitational acceleration is 588 Newton divided by 9.8 Newton per kilogram will give you 60 kilogram. Then you can draw a free body diagram. So you have centrifugal force that is flying you away from the surface because of the rotation. And obviously that centrifugal force is exactly the same as a centripetal force, by the way. Remember that when we did the free body diagram, they cancel each other. Now, so we know that sum of all forces on a y-axis is Fg plus Fn. So Fn now is the reading between those two, the difference between the force of gravity and centrifugal force. So that is equal to mass time centripetal acceleration. So normal force or reading is Fg minus MAC, which is a mg minus MAC. We can factor m, which is a g minus AC, which is 60 kilogram, times now g at the equator level, at the surface of the Earth at equator, is not 9.8, by the way. It is less. It's a 9.78. You can see that in the table. So it's 9.78 minus 0.03374. And if you do that calculation, you'll get 584.8. Remember that your weight was 588 Newton. Now, if you are same person, same scale, but now in a different position, it is on an equator surface, then you see the difference now is 3.2 Newton. It's not a big difference per se, but it's like a 350 gram or something. So you become lighter, you lose weight, 350 gram, less than a pound, just by moving from North America to equator, and you just weight yourself, you'll see that you are lighter. But that's a fake though, because that is just a relative to gravitational pull, not really the mass changes. Mass doesn't change. Mass was 60 kilogram and it is 60 kilogram on equator. Another fictitious force on a moving objects in an Earth rotating frame of reference or a non-inertial frame of reference is called Coriolis force, which is a perpendicular to the velocity of the object in a rotating frame of reference. Now, take a look. The effect of the Coriolis force is not very noticeable on an object moving on Earth's surface, but take a look how they just threw a ball toward each other. But you see that because of the rotating frame of reference, the ball from that reference looks like is bended, is moving at a not a straight line. However, if you see from outside, ball does move at a straight line. The effect of the Coriolis force is not very noticeable on object moving on Earth's surface. So the effect is more noticeable on objects that move far away from the Earth's surface, like clouds. And you're going to see this actually, the clouds are moving counterclockwise on a north hemisphere and a clockwise on a south hemisphere for the same reason, because of the moving further away, closer to equator, because the radius is bigger, the distance from the center of the Earth is bigger, closer to equator compared to closer to poles. So that's why there's a bending that we see from the that frame of reference, from the Earth frame of reference. Now you have a video here that illustrates the Coriolis effect. I'll post that link on the bottom of this video. I'll recommend you actually to watch this video. It's a very good one. Artificial gravity is a situation in which the value of the gravity has been changed artificially to move closer to match the Earth gravity. So there are two ways to do it, either using a centrifuge that I mentioned at the beginning, or using a rotating space station. The rotating space station, it looks beautiful and it looks closer to reality, but it's very difficult to build and manage. Why is that happen? The absence of force against the human body causes the muscles to become weaker because they don't really need to work hard, and bone to lose calcium and become brittle. The heart and blood vessels swell from the built-up excess of body fluids in the upper body because normally under the gravity they are pulled down. In absence of gravity, they are in a normal situation. So that's why astronauts are trained to reduce this negative effect on their body, because while they are in International Space Station, they are going to be on that free fall, on that floating mode. So that's why they are trained, and even in an International Space Station, they have a training tools to make those muscles stronger and etc. Let's do a practice problem with artificial gravity. A spacecraft traveling to Mars has an interior diameter of 324 meters. The craft rotates around its axis at a rate required to give astronauts along the interior wall an apparent weight equal in magnitude to their weight on Earth. Calculate the speed of the astronauts relative to center of the spacecraft. So what do we have here? A radius is half of diameter is 162 meters. Centripetal force has to be equal to gravitational force, or centripetal acceleration has to be equal to gravitational acceleration. So speed is required. So in order to calculate the speed, we use the formula v squared over r, which is centripetal acceleration. In this case, is gravitational acceleration. So we can solve for speed, which is the square root of gr, and now we have both g and r. We plug those numbers and we can find the speed is 39.8 meters per second. B. Determine the period of rotation of the spacecraft. So still we can use the formula that includes period and acceleration. So centripetal acceleration is equal to 2 pi square r over t square, and that has to be equal to g. And then we can solve for t, which is a square root of 4 pi square r over g. And now we have everything to solve. So 4 pi square r is 162 and g is 9.8. Plug those in the calculator and we get period is 25.5 seconds. So one rotation happens every 25.5 seconds. There's a video that I'm going to post a link. That's a very good one, beautiful one to watch, to show you what artificial gravity would look like and what would be a rotating spaceship to make up for that absence of gravity. I'll post that link on the bottom of this video. One of the applications of the circular motion is a roller coaster. Early designer constructed a roller coaster with one circular loop. The roller coaster car had to be fast enough in order to complete the circle without falling. But many people were injured on the ride because of the high speed required. So how can we make a roller coaster that require low speed, but to have the same fun, the same way of riding. So looping roller coaster have the smaller diameter, smaller radius, but the same height. So you're going to have the same fun, but now with a smaller speed, with a safer speed. Now looping roller coasters are designed as a curve with a radius that is longer at the bottom of the loop and shorter at the top of the loop. So it will require less speed, and obviously less speed means it's safer for riders. Now let's do a practice with comparing two design of the roller coaster. The roller coaster car would need a minimum speed at the top of either type of loop to prevent falling down. However, you need a speed to produce what we call weightless or free fall. Calculate the minimum speed for each type of the loop respectively with a radius of the circular loop of 15 meter for older design and for 7.5 meter for a newer design. So what we have, you have those radius, and we draw a free body diagram. You see a force of gravity is toward center of the earth, and normal force, I draw it down because it is on the top of the loop, cannot go higher than that. However, what we need here is normal force has to be 0. So a car has to fly on its own and stay and beat the gravity. So since that center of that loop is down, so it's down. So when you are at this point, the center is down. When you are at this point, the center is down. So that's why acceleration, centripetal acceleration is down. So that will be a positive direction. And now we can say sum of all forces on the y-axis is equal to a force of gravity plus normal force. That is equal to MAC. Mass is mass of the roller coaster, and you're going to see that the mass will cancel. You don't really need the mass because you cannot really design a roller coaster for a certain person. Okay, and then sum of all forces equal force of gravity, which is equal to MAC, because normal force has to be 0. I already talked about it. So you have to feel weightless. And force of gravity has to be equal to MA. So you know force of gravity is mg. So mass and mass cancel. So that's why we have G is equal to AC. But AC is equal to V squared over R. So from here, we can have the G is equal to V squared over R. And then we can solve for V is the square root of G times R. And now we have both. We have a formula to calculate for both design. One design have R 15, so 9.8 meter per second squared times 15, and we find 12.1 meter per second. And for a new design, it's a half of that radius, 7.5, and the speed is 8.57 meter per second. Why is not 5? Because it's square root of it. So obviously it's not really half, but it improves a lot. So from 12 meter per second, and you can do the calculation with a 3.6, it's fast. And the car have to move at a 8.57 meter per second in that loop that is smaller. It will generate more acceleration, centripetal acceleration. That makes you at the top of that roller coaster, you're going to feel that you're flying, you're feeling weightless. That's the whole idea about that roller coaster. And that's conclude this lesson for today, and conclude chapter 3 and unit 1. So that's about it. Have a good one.